Now next issue is elastoplasticity. In 우리말 it is called 탄소성. So elasto means 탄성, elastic. This is 탄성. The plasticity is 소성. Okay, 소성. Now what is plasticity? Plasticity means that if you remove the loading, so we have irreversible deformation. That is the plasticity. So if you keep in the case of perfect plasticity, so if you keep the stress value is the same, so we have infinite development of strain. That is the characteristic found in perfect plasticity. This is a typical simplification of stress-strain diagram here. In reality, the stress-strain diagram is much more complicated. In the case of steel, let's imagine that we are doing a one-dimensional the tension test. This is called dog bone specimen. Stress and strain here. Then if you measure the stress-strain behavior, it looks like this: stress and strain. Then initially linear branch, and then we have yielding, and then we have hardening, and then we have plastic deformation. We have softening here. This is what's happening in reality. So what if you unload, this is loading direction, and if you unload here, okay, unload, then the slope is same as the loading slope, and the unloading slope is the same as the initial slope. And this is then, if you remove the loading completely, we have irreversible strain. This is called the plastic strain. So obviously that description is very complicated. Instead of that, in engineering design, so we simplify the behavior using bilinear behavior. In the case of hardening material, so obviously we have a hardening here. So elastic branch, and then this is called the hardening branch. Okay, this is called hardening branch. And then this behavior is even more simplified. The initial elastic branch, and then perfect plasticity. This is called perfect plasticity. 완전 소성. It is called 완전 소성. Okay. All right. So here, in the case of perfect plasticity, the stress is limited by the yield stress value. That's why the stress calculated by this flexor formula should be limited by what? The yield stress value. In the case of perfect plasticity, the bending moment produced by the plastic behavior. If normal stress touches to the yield stress value, we call it critical bending moment, which causes the plastic behavior now. Okay, this is the evolution of stress distribution in the cross section. If you consider the plastic characteristics of material. Initially we have linear elastic behavior distribution. So this is my neutral axis, and then as we increase the loading, and the stress eventually becomes equal to the yield stress value. Sigma is equal to the yield stress, and then after that, stress cannot increase, exceeding the yield stress value, because the material behavior is limited by the yield stress one. So we are using the perfect plasticity. And then to satisfy the moment equilibrium, the position of neutral axis changes. Okay, changes, and then eventually the elastic branch disappears. The whole cross section, the stress in the whole cross section becomes the plastic state. This is called the situation here is a plastic hinge. Okay, plastic hinge, because once it reaches the perfect plasticity in the cross section, then we have the rotation in this cross section. That's why we call plastic hinge. It is called 소성 힌지 상황. 소성 힌지 상황. So let's consider the internal forces in the plastic limit state in the reinforced concrete problem. Here, let's consider a reinforced concrete cross section here. Then it's a simplification. We have compressive force and then tensile force here. And then in the sense of force equilibrium, so we can consider three different cases. If the coefficient K is equal to 1, then in that case we have the compressive force is equal to the tensile force. This is called the pure bending situation. If K is equal to 1, then because tensile force is greater than compressive force, this is a tension bending problem. If the coefficient is less than 1, is greater than 0, this is the compression governing bending problem. So in that case, we can decompose the problem into two. Make sure that we are using the principle of superposition for only the internal forces. So we consider combination of the symmetric loading and then anti-symmetric loading here. So we decompose K, the tensile force, half of it here, and also half of it here. And then we consider, to satisfy the force equilibrium, we consider remaining half, and then because there is no tensile force here, so we cancel the tensile force considering the opposite direction. Then this is cancelled. And then compression force too. We consider half of it here and another half, and then to satisfy the force equilibrium, so we consider half, but in the opposite direction half here. Then if you superpose all these internal force components, it satisfies the original configuration here. Then if you look at here, that produces what? That produces the compressive force, isn't it right? That produces compressive force. And then this produces what? Tensile force. And then this produces what? The bending moment produced by the compressive loading. And then this moment, this is what? Bending moment produced by the reinforcement. Then we can decompose this problem into the actual force and then bending moment when we discuss torsional or plastic state in the reinforced concrete cross section. And then maybe at this moment it is very hard to understand the concept of this diagram, but please keep in mind this diagram until you take the lecture of reinforced concrete design, and then it becomes very useful. Okay, let me stop my lecture here. So if you have any questions, you may send me your question into my email here. Okay, thank you.